guys, let's see the how derivative works. Okay, basic we can say geometrical meaning of derivative. So as you can see this diagram I have drawn here, there is a point P which is here and there is a point Q. Okay, and if basically we are moving from, let us suppose, you can assume yourself, we are moving from point P to Q, definitely there will be change in dimensions from N. If horizontally if I'll see, so you are moving from M to N, and for vertically you can say that you're moving from L to O, the extra distance which you are moving here. So that's why derivative is basically, I told you already, the change of function with respect to another variable. It means here change in QL because of change in PL. So we can say that if QL is y and PL is x, so we can say dy by dx will be my derivative for this change in PQ. Okay, so as you can see here, I have written the point P as f naught and x f of x naught. So don't get confused with f of x naught. So P point we can write like this also, x naught and y naught. Okay, because y is nothing but my output, and we can, in terms of output, some if I want to represent my equation in terms of output, I can write as y naught x f of x naught. Okay, both things are same only. Similarly here I have written here this q as, so x naught plus h and y naught plus h. Okay, what is this h? Basically the parameter which is changed because of moving from point to Q. Okay, the values, the change in values of the dimensions, basically you move from P to Q. Okay, so now what will happen is, now if we want to find a derivative here, or if we want to represent our differentiation here, so what we will have to do is we have to find the slope or the gradient. Okay, so gradient in that case we can say that this is my Q function, and this is my y axis, or we can say the y value, and this is my x value. Okay, so if I want to find, so I will do that like differentiation of y with respect to x, or we can say the differences of y naught with respect to x naught, or we can say that differentiation of y naught plus h with respect to x naught plus h. Okay, this is what my I'm representing derivative. It means my change in the dimension, change in y naught with respect to x naught, or change in this. So basically this is representing the instantaneous change, or this is nothing but known as a slope. Okay, the gradient. So the gradient, one more thing, if you know about that, in a if I'm talking about a line, so at a line the gradient is same everywhere, the slope will be same everywhere. Okay, means slope is also represented by the theta, tan of theta. So here if my angle is psi initially, so tan psi, so wherever you will take this angle tan psi, even though here at this point if you will take the angle as psi, at this point, as you can say, this angle here already mentioned here as psi, so it means my derivative will be same at that point also. It means my slope will be same at that point also. Okay, so we have worked out for this. Now you can see that tan phi, I'm finding a tan phi from the figure. We can see that tan phi is nothing but QL by PL. So tan phi here, this is in the triangle, you can say that P here, this is my R and this is M, and my PL is nothing but equal to MN, and my PM is nothing but equal to NL. So by that I got from this triangle, using the trigonometric ratios, I got tan phi is equal to QL by PL. Okay, now QL can be written as NQ minus NL. As you can see from the diagram, we have a QL can be written as this QL, basically can be written as NQ minus of NL. We can write this QL as it is. So NQ minus NL by M. So what is NQ minus NL? The change in the function, which is nothing but f of x naught plus h. And what is my NL, or basically MP, we can say that by f of x naught. And in denominator, the change in my horizontal values is this. Okay, so by this what I got my tan phi as the f of x naught plus h minus f of x naught divided by h. So this is nothing but my known as my slope, or my derivative, or my gradient. So you can say this is a geometrical meaning of my derivative. Okay.